2,000 subscribers. I said when we hit that, we would do some more multiple choice questions. So I thought maybe this would be a way of doing it. Instead of just putting out a multiple choice paper, I could pull together a load of questions that people have sent in. This one is going to be mainly based around weldability. We could bring up the question, talk through, decide on the answer, and then I'll try to explain how I would get to the answer and anything that goes around the side of that subject. With all of these, I'm seeing a pattern of people just saying, I want multi-choices, I want multi-choice. Right, that's great and that helps a lot, but just learning a multi-choice question and the answer is not going to help you with your examination. There are thousands of questions in the bank of C-SWIP questions, right? You will not remember them all. So what we need to be able to do is use a question as a trigger to jump onto the train and then work out where we need to be along that train and be able to answer any question that comes. So an understanding of the subject is important here, especially with leading questions where the question paper asks you one to start and the answer from that first question is the precursor or the next answer for question 2. If you can't understand the whole process, they become really, really difficult. But at the same time, don't let these leading questions put you off. They are literally one question, one answer, another question, another answer. They're just saying that tide to make more questions. Just see it like that. Every question should have an answer, and we go from there. Before we start, like I say, 2,000 subscribers, amazing. Was never intended, so thank you for your support and the drive to keep watching our videos. I get the stats now, through my YouTube app saying, over 1,000 people a week are watching videos from all over the world. Hundreds of hours of watch time, which is just blows me away. It still feels a bit weird saying that. Have a look at our channel update video, which will be coming out. So this is the 31st of December 2024. As we go into 2025, we're going to be doing a lot more. So have a check out of the channel update video about what we're going to be doing this year and how things are evolving very, very quickly. A reason why we've been away for a while and we haven't done as many videos. But yeah, thank you very much for your support. Keep it coming. If you can share the video, if you can share what's happening with as many different people as possible and just get them to start watching the content, that allow us to do more videos and keep driving and try and get partnerships with different organizations and stuff so that we can give better explanations about how and why what happens in our industry and the technologies and the metallurgy do what they do, getting involved with some really cool people so that we can bring more information to you in the future. So it's free. Just hit the sub button, watch a few videos. If you're in a chat room or anything like that, on Facebook or Discord or whatever, just share the link and hopefully we can get more people through. But with that, let's have a look at some questions. So all of these questions have been sent to us by people all the time, and I've just gone through them and tried to pull a load of weldability questions together for this. So the first one here is, what is weldability? Right. Weldability is a term which we use to describe how difficult something is to weld. If it's easy to weld, we don't need a lot of control. If it's difficult to weld, we'll need a lot of precautions, like lots of preheats, cooling rates, maybe different materials, maybe a drop or an increase in heat input. Maybe we're limited to welding processes, so all of that happens on the hard end of things. But on the easy end, the good weldability, we can just weld it and it'll be fine, right? So first off, our answer here is the ability to be joined by welding. Okay, so weldability is a scale on that ability for us to physically join something. This ties very closely to this diagram. Now, you may have seen this diagram a lot for those who are just listening, because I'm told there's a lot of people who just listen as they're driving and things. This is a table or a graph where you've got an X and a Y axis. Along the bottom axis, you've got your carbon percentage increasing from 0 up to, on this case, 1.4. And then we have tensile hardness and elongation values going up the vertical axis. Okay, what we see is as carbon increases, tensile strength goes up. Okay, at the same time, hardness values go up. Now, this graph shows as Brunel hardness. I prefer to work everything with hardness figures, but it's the same sort of pattern. Tensile strength's going up, hardness is going up. Elongation, so elongation being a measure of ductility, that's coming down as hardness goes up. So the harder something is, the higher tensile strength it has, the less ductility it has. Now, when we get to around the 0.8 to 1% mark, tensile stress starts to drop, because what happens here is there's so much carbon in the system, the grains just don't hold themselves together anymore. So that falls down, and we then lose tensile strength even though hardness keeps going up. But to about the 1% mark, tensiles and hardness values stay close with each other as they head up and through. Okay, so the more carbon content we've got, the harder it is to weld. Now, other questions that come in around this are things like, what is the term for the ability of a material to be welded without cracking? So that would be weldability. So same answer, different way of questioning it. Of course, because we've got that increase in hardness, the lower the weldability, the more likely it is to crack because it has a higher carbon content. Carbon has the greatest influence on hardness, right? Strength is always there because we add carbon to the system in order to give us strength. But really, we're worried in weldability about the hardness value of that grain structure that it produces. And then an increase in carbon will require an increase in preheat. Yeah. So by far the biggest control we have here is as carbon content goes up and weldability comes down, we increase the preheat value to get more heat into the structure, so it cools slower and therefore is less likely to crack. So, second one, which factor does not affect weldability? Now, I've seen this question around quite a lot. It's a difficult one because I would potentially err on the side of everything affects weldability to a degree. But if you get a question like this, which is the least likely would be a good way of answering it. So how could we look at this and drive this forward? So which factor does not affect weldability? We'll have material composition, welding process, ambient temperature, or welding position. Now, if we've already decided that weldability is the process in which we join materials, and a good weldability has less control, and a lower weldability has more control, we can kind of use that to say, well, if I change these, what's likely to happen? So which of these factors does not affect weldability? So I would go with ambient temperature as a sort of like, oh well, which one makes more sense out of these questions? Okay, and the reason for that, if we look at material composition, right, that is instantly triggering, well, what's the alloying content? Something that has a higher alloying content might have more carbon content, and therefore goes back to that previous graph. So that's, material composition is always going to affect weldability. It's just they go to there. Welding process, different welding processes might affect the amount of heat inputs they produce. And if we're talking about preheat levels and weldability and heat into that process to stop it from cracking, welding processes, some materials just won't weld with certain welding processes, or they're easier to do with others. So I would say definitely the answer is not welding process. Ambient temperature. Okay, you could say, well, if I've got a low ambient temperature, I'm going to need a bit of preheat. But I guess that's for all materials, whether they have good or poor weldability. You often want to get them above 10 degrees before you weld anything to stop thermal shock and distortion issues and things like that. And the last one here, welding position. Well, welding position might be welding processes, preheats, heat inputs. Some welding processes won't work and things like that. So the best answer here, I would say, is ambient temperature. It's not a great answer, but it's the best one. Okay. Which material is generally considered to have good weldability? So we've got cast iron, stainless steel, aluminium, and titanium. So again, weldability, the process in which we join materials together to have low control and get a good result, or lots of control to have a good result. Which one would be? Well, cast iron, what would we say? Is that going to have a good weldability or poor weldability? Well, it's got a high carbon content, multiple percentage points of carbon. Therefore, it's probably a low weldability. If you try and weld cast iron, very often it cracks, and that's all. It doesn't work. You need very, very high heat inputs, very, very slow cooling rates to really have a chance. And some grades just won't weld at all. Stainless steel and carbon steel, your standard carbon manganese steels, really quite straightforward for a lot of the lower strength value ones. So stainless steel, okay, you might need to back purge the back of root runs and things like that, but really we have quite a range of welding processes that can be used. We don't need to preheat because there's a very low carbon content. It's just generally quite an easy thing to weld without cracking. Okay, because that's weldability, remember, the ability to weld without it cracking. Aluminium, some grades of alloy just don't weld, I think like the 7000 series and stuff like that, we see them as cracking fairly easily because of hot cracking. Titanium, stainless steel, titanium are they fairly close. I would say that titanium needs a little bit more control, because you've got not only the purging issues to stop it oxidizing, but also the cleanliness issues to stop porosity and things like that. Any contamination, titanium tends to cause us issues in the process itself. So my best answer there is stainless steel being good weldability. And here on the list, we've got just some examples here of the different things that I think I've talked about there. So cast iron, poor weldability, high carbon content. Stainless steel doesn't need preheating because it has a very, very low carbon content, especially if it's a 316L or something like that, low carbon grades of stainless steels. Aluminium, some of them hot crack, 7000 grade doesn't weld. because it has hot cracking issues. Titanium, a lot of things around it to keep it clean, oxidization free and stuff like that, so that's relatively difficult. Okay. So next we have, what is the main concern when welding high carbon steels? Now again, these questions have been sent in to me. I would maybe reword this and say, what is the main concern when welding high strength carbon steels? So we've got, here is the answers. What we got high melting point, formation of brittle martensite, a low thermal conductivity, or a high electrical resistance. So, right, high carbon content. Best thing for us to go with here is probably high carbon content, more likely to produce martensitic structures. Okay, so the answer here would be B. Now, if you want to know more about this, you need to learn the time temperature transformation graph. If you've been on one of my courses, you know I love this graph. I think it explains a lot around things like weldability, hydrogen cracking, things like that. The reason we have a lot of controls in WPSs can be explained through a TTT diagram. And we already have a video on our page, effective cooling and its effect, TTT diagrams 101. But basically what happens here is, as carbon content increases within a material, the martensitic band of that TTT diagram will increase. It gets longer. It pushes the whole graph to the right. This means that for the same heat input to try and get a pearlite, ferrite, selenite structure, good grain structure, we're going to need to have a much longer cooling time. Okay? So we will have to have a higher preheat value as we fall into that. So high strength carbon steels, generally high heat preheat values, slow cooling rates. Which welding process is known for its high weldability with most metals? Okay, so which welding process can we use across most materials relatively easily? Now, my answer here would, the answers first, if you're just listening, as gas tungsten arc welding or TIG, shielded metal arc welding or MMA, gas metal arc welding, so that's your MIG-MAG, and flux core arc welding. Right. I would say the welding process that can be used over the widest range of materials most easily is TIG welding, so gas tungsten arc welding. The ability for TIG welding to be able to use filler wire or no filler wire is second to none. Because it allows us to weld materials where maybe they're very thin, or we don't have a filler material to join them, or adding a filler material might cause issues. Lots of different things here. But here on the slide, you will see a list of 7 reasons that TIG welding is generally good for most things. Problem here though is the deposition rate. So the amount of weld metal we produce per hour is tiny compared to the rest of the welding processes, and of course that's going to cause an issue when we look at cost. Okay, and it has a higher skill level compared to the other welding processes, so cost goes up again, skill and time. So efficiency is relatively low. Okay, but generally, when in doubt, TIG weld it, and you should be able to control the processes enough from a weldability issue to be able to weld a material. Next one. What is the effect of sulfur and phosphorus on weldability? So will they improve weldability? They have no effect. They reduce weldability, or they only affect weldability at high temperatures. So they do have an effect on weldability, and they're for two different things, okay? But they're going to reduce the weldability of our material, okay? I think here I've got phosphorus, okay? It's a residual element, which means we try to get rid of it as much as possible, right? The thing here with phosphorus is once we weld it, it generally produces what we call cold shortness, which is when we take a material and we try and form it, we try and bend it through, say, 90 degrees, and they crack, okay? High phosphorus materials, we don't really want that. Now, sulfur connects into a lot of failure mechanisms in different ways, okay? The most common one we talk about sulfur with is solidification cracking. And again, we try to remove sulfur in weld steels we know we're going to weld as much as possible. And this is where a lot of cost enters the system in steel manufacture to drive the sulfur level down. So sulfur mainly is solidification cracking, but has play in laminar tearing and sort of inclusion creation and stuff like that. Yeah. Solidification cracking, laminar tearing, inclusions, sulfur, non-metallic sulfur is our issue. Yeah. Which of the following is a common weldability test? So before I sort of give an answer, right, yet again, ask the question, what is weldability a measure of? It's the ability to weld it without cracking. Why do we get cracking? Well, we get cracking because we have a high carbon content, which then leads to potentially a martensitic structure, which is more likely to crack. So hardness values go up with a martensitic structure, right? What test is going to find hardness values? All right, our answers here are tensile test, Sharpie impact, bend, or hardness tests. Yeah, so because we go through and we understand the process of what weldability is, we just know it's a hardness test is going to be the answer, right? But again, on the slide here, we've got tensile tests. So tensiles are used to understand yield, tensile, and elongation of materials. Sharpie impact tests are used to understand the transition point between ductile and brittle materials at a test temperature. So we have a dropping temperature, which then finds that point at which it becomes brittle, and we don't want to go past that. We've got our bend tests, which is a qualitative test used for understanding ductility, and our hardness test, which says, okay, how hard is this material after welding? And we can test in the base material, the heat affected zone, and the weld metal. Our different standards give us different amounts of levels for this. You know, if you look, say, in 15614 and the ISO spec, it's saying a hardness value of 380 for sort of normal materials. So use normal carbon steels. Can't go above 380 because it hardness figures, because at above 400 we're likely to have martensitic structures. So we can hardness test something, and if the parent material is really hard, the probability of weldability being poor is increased. Okay, so what is the primarily I can't even say it, you know. What is the reason for preheating before welding? So slowing the cooling rate, if we think about a TTT diagram, is going to push us into the pearlite, ferrite, and semonite regions. We don't want to get into martensitic regions. So preheating adds heat, which slows the cooling rate. That can be helped if we then add blankets on top of things and try and keep the heat in for as long as possible. But by slowing the cooling rate, by keeping away from the martensitic regions, we are going to reduce the risk of cracking. Yeah. Some materials like a 690, you're going to need to have a high preheat and a very slow cooling rate. So you put a relatively high preheat in place, you try to weld it relatively hot, and when you finish, you cover it in fire blankets and you keep it and you just let it cool over hours, maybe a couple of days, and then take the blankets off, and then hopefully it hasn't cracked. Yeah. So again, slowing the cooling rate. Think of our TTT diagram and how that's affected by carbon. As carbon rates go up, the TTT martensitic band gets bigger, and we need to slow cooling more, right? Now, preheat is calculated using 4 different things. Okay, so material thickness, because the thicker the material, the faster it will cool. Now, we use a term here called combined material thickness, which is measuring all the heat paths away from the weld itself. So if you have a butt weld, you have 2 material thicknesses, so your combined thickness is 2 times the material thickness. If you have a fillet weld, it's 3 times the material thickness. Okay, the heat input that you're going to put into the steel when you're welding, and then the hydrogen scale, which is a factor of the welding process, which tells you how much hydrogen is likely to be produced during that process. Okay, so if you use all 4 of them, you can use a standard called EN 1011, which will then give you a preheat value, which then helps you reduce the risk of hydrogen cracking and brittle materials in general. Okay, here we've got one which is, which alloying element is known to improve the weldability of steels? Now, weldability is the ability not to crack, so we want to reduce the amount of carbon in our system as much as possible, and we do that by using manganese. Okay, so your carbon manganese in your system means you can get more strength but reduce the effect of hardness on our process. So on the slide here we have the main elements we have and we think about in carbon steel. So iron is, it's all right, but it's not good enough. It doesn't have a high enough strength for engineering. So we need to add carbon in. Now, the way I describe this is like, right, if everything was just iron, it's like your body without the skeleton. It'll just be a pile of flesh on the floor. Not the nicest thing to think about, but we're not very useful. Yeah. So we add a bit of carbon, we add a skeleton to our steel, which then holds that soft material upright and allows it to move and have some structure. So now we have the best of both worlds. We have the malleability of the iron, but the strength of the carbon. But if I keep increasing carbon content, I keep increasing the skeleton in my body, eventually what will happen is I just become too rigid. I'm too hard, I'm too rigid, I can't, I've got no ductility, I can't bend my arms and move around, so I'm then useless, right? So what we do is we add manganese in the place of carbon, up to about 1.6%. And that increases strength, but has 1/6 the effect on hardness than the carbon. So gain strength, but not as much hardness. Okay. Silicon is a deoxidizer. It's a general deoxidizer we put in most things. It captures oxygen and stops porosity and things like that. Phosphorus and sulfur we've already talked about. Another answer on this list is chrome. So chrome is used as an environmental corrosion protection. So in stainless steel, we have chrome and nickel. Chrome is for your environmental protection. Nickel is for your acidic attack. So by having them two together, it doesn't rust in the air, but then it doesn't rust or isn't corroded by acids and stuff in production in petrochemical plants or pharmaceuticals and stuff like that. So generally we add manganese to increase strength without increasing toughness, without increasing hardness, and therefore we maintain weldability. Okay, so that is our sort of few questions on weldability. You can see we're always thinking about what is the effect of what I'm doing and how is it going to increase the likelihood of cracking. So if I increase carbon, I increase cracking potential. If I drop out the carbon and replace it with manganese, I'm more likely to have strength with the reduction in carbon content. Yeah, so that's how we look at carbon, how we look at weldability, and how we then drive forward the changes in our process to be able to reduce cracking. Okay, so with that, if you've got any more questions on weldability, drop them in the comments below. I will answer as many questions as possible if they're in the comments, right? If you have a question, somebody else probably has the same question, so it helps everybody if I'm able to answer them together. Okay, and it really helps the video, the more comments and all that. The algorithm loves it. So any questions down below, and I will see you in the next one. And good luck with your studies.